Okay. Hello everyone. So my name is Rajendra Reddy Mallepalli. I'm working as a research assistant professor at Department of Chemical and Life Science Engineering, Virginia Commonwealth University, Richmond. I hope you all can able to see my screen clearly. If not, please let me know. So before going into the details, I'd like to talk a little bit about my background. I'm a chemical engineer by training. I did my B.Tech Chemical Engineering from Osmania University, Hyderabad. After that, I went to Germany for Masters and PhD. I finished my PhD in 2009, then came back to India, worked for 2 years in Dr. Reddy's laboratories, Hyderabad. And since 2011, I'm working here at VCU on like a fundamental chemical engineering, doing fundamental chemical engineering research. And today I'd like to talk about the thermodynamics, the equilibrium properties like phase equilibria and density, how to measure them experimentally, and how to predict using equation of state models that we teach to the students in third year or final year. Okay, this is a picture of downtown Richmond. So here, like the VCU School of Engineering, this is one building and there is one more building on this corner. It's not showing in the picture. And there are a couple of other buildings here belongs to VCU, but most of this stuff is like a downtown Richmond. It's not part of VCU. Okay. So why do we need this phase behavior and density data? So these kind of studies and the information is really important for process design as well as for model development. And especially process design, I mean like a manufacturing of polymers and pharmaceuticals. So here the polymers are used in many applications in our daily life. Like you see, like they can be made with bottles, tubes, sheets, many more. I mean, just here a couple of examples. So most of these are made with simple polymers like polyethylene or polypropylene. So those polymers are made at really high temperatures and high pressures, and it's important to understand the phase behavior and the density information for process design calculations. So here I like to start with a pure component, carbon dioxide phase diagram. So this, like here I'll show this as a video. I took this video from YouTube. So if you are interested to show this to your students, you can always download from YouTube or directly broadcast from YouTube, but always show this reference link so that we're not infringing anyone's copyright. So this video is made by this company Danfoss, so they're refrigerant manufacturers, and here what they so what you're seeing here is like a in a high pressure cell, liquid CO2. This is the bottom thing, and there is a like a phase boundary. Then there is a vapor phase. So there are like at these conditions, both liquid and vapor of one component are in equilibrium. So what is the equilibrium criteria? Like in the thermodynamics, we study viscosity of vapor phase is equal to the viscosity of liquid phase. So when these conditions are met, both liquid and vapor are in equilibrium. So now as we go, I'll skip some of the This video is too big. So here, this is a PT space, the pressure temperature axis, and the temperature is in degrees centigrade and pressure in bar. So depending on the temperature pressure conditions, the substance can exist in different phases. Like for example, at room conditions and atmospheric pressure, this is CO2, like everyone knows that CO2 is a gas. But at room conditions, for example, at 100 atmospheres or 100 bar pressure, CO2 is in the liquid. So similarly, like at negative temperatures below 56 degrees C, and then pressures 5 bar, close to 5 bar, CO2 exists as a solid. So this is we call dry ice for packaging or for many refrigeration applications. And then there's one more phase, like there's 3 phases: solid, liquid, and vapor. We all know and we study this. And there's a 4th phase called supercritical phase. So what is this phase? So as you see here, this line is the phase boundary between liquid and vapor. So, but when you go into the supercritical phase, so this phase boundary is kind of cuts off. So that means there is no distinction between a liquid and vapor. So this is called a fluid. So and then there is a solid and vapor equilibrium curve and a solid and liquid equilibrium curve. So under the supercritical conditions, like how do we generate? Let me show a couple of other. Yeah, here this is for a triple point. What they are trying to show here is, like, you start out at this point, atmospheric condition, like a room temperature, and the pressure is like 56 bar, that is CO2 vapor pressure. So you're filling the high pressure cell with CO2, and as you see, the liquid level is moving up. And then once you put sufficient amount of CO2, what you do is your starting point is here, and then you slowly open up the vent. So that means you are reducing the pressure. So you're going along this vapor pressure curve. So you hit until you hit the triple point pressure. See this how CO2 is evaporating with bubbles. So what is happening here is like CO2 gas, like we opened up the outlet valve, so CO2 is going out of the cell. As it is going out, some like this, it cools down. This is called a Joule-Thomson effect. And then it cools down, and the temperature reaches to like all the way to the triple point conditions. Then you see the formation of the solid. See right here. So this is a triple point of CO2. Pressure is 5.2 bar, and temperature is minus 56.6 degrees C. So at this particular temperature and pressure, the 3 phases of CO2, vapor, solid, and a liquid, are in equilibrium with each other. So If you remember, like the Gibbs phase rule, the components plus 2 minus 2 is equal to the degrees of freedom. So you have one component, so 1 plus 2 equal to 3 minus 3 phases, solid, liquid, and vapor. So 3 minus 3 is 0. So there are no degrees of freedom. So this is a one particular condition that a single component can exist. So there is no other uh, uh, parameters for adjusting. Okay, so and then what happens again if you reheat it? So the solid CO2 becomes like a liquid. It's I'll move forward a little bit faster. As you're heating up, again you're going along the vapor pressure curve. Then see the solid CO2 turns into liquid. And then again liquid and vapor are in equilibrium. As you go. Now let's see the critical point. Again you start with a critical point of CO2 is like 31 degrees C and 73 bar. This is a density temperature diagram and okay. So inside the cell again it's a similar experiment. Now at room conditions they're loading CO2 into the high pressure cell. As you see the liquid level is going up, and once you're done with the charging, then what you do is, like in this case, instead of opening the valve like here, you heat it up. So as you heat up, so what is happening here is like here at room conditions approximately 20 degrees C, and then you heat up to go to like greater than 31 degrees C, and right around critical point you see that there is no like the phase boundary, like that line that you saw, liquid vapor. So there is no, so that means there is no distinction. It is like a single fluid phase. And the critical point 73.6 and 31 degrees C, then you won't see the phase boundary. So we are in the supercritical region. And again from the supercritical phase, as you see here, your starting point is here. As you drop the pressure and temperature, again you see the both phases, like two phases, gas and liquid, will end up with your starting point, like the vapor and liquid. So the point of showing this video here is like it's always useful to show to the students, like they can imagine like what is the pure component phases looks like and how to generate those phases. It gives some kind of interest to the students. So what are the properties of this CO2 that are really important? And in the supercritical conditions, the CO2 density is more like a liquid density. So that means the molecules are close enough that they act as a solvent for many industrial processes. And the CO2 viscosity is like a gas. So that means the diffusion kinetics are very high. So the rate of diffusion is faster. And the applications are like there are plenty of applications for this solvent, since the critical conditions are moderate at 31 degrees C and 73 bar. You can go to the supercritical phase, and it's used as a solvent, and it's called like the processes are called green processes. The reason is like once you're done with your process, what you do is like you depressurize the system, and then all the liquid becomes like a gas, and then the gas goes out of the system, so that means there is no residual solvent. So for pharmaceutical applications, and there's due to the stringent government regulations, using this kind of solvents it really benefits the processing. Then the CO2 is mainly used as an extraction solvent, and what the main application that is developed in early 1980s is decaffeination of coffee beans. So that's the main, and now the applications are increased to many natural processes and many flavors, and also it is used as a solvent for synthesizing the polymers and some pharmaceutical compounds. And in our lab, what we are using CO2 is for synthesizing a materials called aerogels. We start out with a hydrogels. This is filled with a liquid, and then we replace the water with alcohol that is more miscible with CO2. And then using the supercritical CO2, like we start out at this point A, there's an atmosphere like a 20 degrees C and the vapor pressure of CO2, and you increase the temperature and pressure to go into the supercritical phase. So under supercritical conditions, CO2 acts as a good solvent, and it dissolves all the solvent from the waves. Then once you are done with your process, and then you drop the pressure and then cool it down. So then you ended up with a materials called aerogels. These are like a high surface area materials, and supercritical drying is really important for this, retaining the porous network in this material. If you do the regular vacuum drying or some ambient drying, then you lose all the porous network in these materials. So the properties of aerogels are they have very high surface areas, goes to 600 to 1000 square meters per gram, and pore sizes are 25 to 30 nanometers. Pore volumes are like 2 cc per gram. So here is a typical example of pore volume versus pore diameter. Then there's a typical scanning electron microscope image showing the porous network. And we did many kind of aerogel materials using biopolymers. And then our main applications are for controlled drug delivery. Like what we do is we make the aerogels using supercritical CO2. Again, using the supercritical CO2, we load the drugs into the aerogel material, and then show that aerogels as drug carriers. And the people also have done the aerogels as a catalyst support, since they have a very high surface areas, and they are very good insulation materials. So there are many applications now in investigation, for house, for domestic purposes, doors and windows. In cold countries, that saves a lot of energy. And then high temperature ovens, like the window, the door panels. And undersea oil pipelines are insulated with the aerogel sheets. Then the NASA, the US Space Agency, they use this aerogel material as a spacecraft insulator. And you can find more information on this website, aerogel.org. Now, let me show you the real equipment that we use in our lab. This is one of the phase behavior and density measuring apparatus. The one is like a boroscope that is used to look inside the cell. So when the cell is under pressure, it's really dangerous to look with your eye. That's why we use the boroscope and the camera that is connected to a computer monitor, so you can see what's going on inside the cell. Then the 2 is a high pressure view cell. The 3 is, here is a LVDT. LVDT is a linear variable differential transducer. So this, what it do is, so it tracks the position of the piston. Like imagine like it's a movable piston is inside the cell. I'll show you a schematic here. So in this schematic, so here is the boroscope that is used to see inside the cell, and there is a sapphire window, so clear glass. Then this is the cell internal part, and this thing is a metal bellow. It's like you can imagine like a movable piston. The front end of this bellow is connected with a rod. That rod back end is connected to a sensor element. It's a LVDT sensor element. As this bellow moving back and forth, like when you're going back, then you're depressurizing, then the position changes. So you kind of track this position of this front end very precisely up to like a micron level. So how do we use this equipment for phase behavior and density measurements? So we need, for phase behavior is like for looking into vapor liquid, you can just use the boroscope camera to look like where the bubble is forming. But for density measurement, you need a calibration. So how do we make the calibration? This is like a inside of the cell, looks like it's pretty clear, and then you see that there is a bubble. So this is like we record this as a bubble point. I'll show you in a minute, like the video how we record this. Then for the calibration, so how do we, like we know density is like a mass divided by the volume. So by knowing the amount of mass that you are putting into the cell, and you should know the volume of the cell. So to know that volume, so what we do is we put a known fluid whose density is already known at all temperature or pressures that we are interested. Then we put that a fixed amount of that fluid, and then we take it to certain temperature pressure. Then at that conditions, we record the position of the sensor, that is this x-axis, and then you pull the density of that fluid from a literature, and then you know the density and you know the mass, so you kind of calculate the volume. So that is this volume on y-axis. Then you generate this like each point at a different pressure and temperature condition over the entire range of this LVDT reading. So once you generate this calibration curve, now you're done. So what you do is you put an unknown, like a fluid of unknown density. So where you should know the exact mass to a milligram accuracy. And then, so once you take it to a certain temperature pressure, based on the position of the sensor, you can read the volume of the cell. So you get the volume and you know the mass. So mass divided by the volume gives you the density. And this you can do even at a high pressures. Like a high pressures means really like going to 3000 bar pressure. Okay, this is a video here. I like to show you the bubble point measurements. So it's like when you look this, it looks like an empty cell. Actually, it is. Now this cell is filled with a hexane plus propylene mixture. Hexane is a liquid at ambient condition, and propylene is a gas. We take it raised to high temperatures. Now this cell is at 150 degrees C. Then, as you see here, there is a bubble. Like let me go back. And this is like a single phase. So you start out in a single phase, and you slowly drop the pressure. As you drop the pressure, so you hit the bubble point. So you saw the single bubble. Then as you keep on dropping the pressure, you see you get more and more bubbles. That means you're going more and more deeper into the vapor liquid region. I'll show you the phase behavior curve plots in the next slides. So you see the more bubbles are forming. So the bubble point pressure for this system at 150 degrees C is like 650 psi, where the first bubble is appeared. So we record that pressure as a bubble point pressure. And then at one temperature, so you repeat a couple of times, like 2 or 3 times, to see the consistency and accuracy. And this is a pressure temperature diagram for the hexane propylene binary mixture. So on the x-axis, temperature in kelvins, and on the y-axis, pressure in megapascals. So megapascal conversion is like 1 megapascal is equal to 10 bar. So for example, at let's say 350 kelvins, and here, okay, let me explain the curves. The curve number 1 is pure hexane vapor pressure curve, and as you go like 2, 3, 4, 5 as different, increasing the propylene content in the mixture. So 2 is like a 14 mole percent, 45 mole percent, 60, 90 mole percent, and 6 is the pure propylene vapor pressure curve. So this is not a typical diagram that we see in like a thermodynamic textbooks, like we see the pH diagrams that I will show in the next slide. But this is quite common for experimentalists to get this bubble point curves, because it's rather easy to record the bubble points compared to the dew point. So here at 350 degrees Kelvin, like if your starting point is here, like a single phase, fluid phase, like a liquid. Then as you drop the pressure, so you hit the bubble. This is the first appearance of the bubble. Then as you keep on dropping the pressure, you go more and more into a liquid vapor. So in every loop, like you have inside of this curve is a liquid plus vapor, and on the left side is a fluid phase, liquid phase, and on the down right side is a vapor phase. But for a pure component, you have only like two, so the liquid and vapor. So here, what is this curve? Like, so we know this. These are all bubble points. So at one temperature, take the cell to this temperature, and you start out with a single phase, and then drop it and get a bubble point. For that, you move on to the next temperature, then next temperature, and next temperature. And here the filled symbols are mixture critical points, and the solid lines are calculations. I'll show you what the calculations are with the equations of state model. And then we published this recently in Journal of Chemical and Engineering Data. And if you have access to this journal, please take a look. And here is okay. This is, let me go back here at a fixed temperature. So if you draw a vertical line like this, so then at all compositions, you can read the pressure. Okay, this is my pressure. This is my bubble point pressure. This is bubble point pressure. This is bubble point pressure. So you get P versus X. So that's what here it is showing. So the propylene mole fraction on the x-axis, on the y-axis is pressure, that's in megapascals. So these are the typical curves that we show to the student in the like a thermodynamics class. So this is at low temperature, like 323 Kelvin, it's 50 degrees C, and this is 150 degrees C. So at 50 degrees C, you see that, okay, the curve is completely hitting the 1. That means the propylene, it is going to hit the pure propylene vapor pressure. So the 1 is pure propylene, that means hexane is 0, and here is hexane pure hexane. So pure hexane at 50 degrees centigrade, the vapor pressure is really low. So and the blue curve is a bubble point curve, and the red is a dew point curve. Then at a higher temperature, so you see the again the bubble point curve and dew point curve, but it's not hitting the this axis. That means the mixture critical point is like above this overall solution concentration. It's like a single phase. So here, like you start out at a liquid single phase, then you drop the pressure, you hit the first bubble, that is like a bubble point. Then you keep on going, so you go more and more into the liquid plus vapor boundary. Then as you drop, you hit the saturated vapor pressure, saturated vapor curve. Then as you keep on going, you go into completely vapor phase. And for this system, it's this, and for this, the vapor is here. Okay, and then it's the reverse phenomena is like if your starting point is here, as you go up with the pressure, you compress the system. As you're compressing, you see the first dew formation. It's entirely like a gas or vapor, and then we see the first droplet of liquid formation. That's we call as a dew point. It's very hard to measure these dew points, but people have done it. Our lab specifically focuses on getting the bubble point pressure. And once you measure the bubble point pressures, what we do is like we use an equation of state model. Okay, here let me talk about this is a tie line. So this is your overall solution composition is, let's say, 50-50. When you are at these conditions, like the temperature is 150 degrees C and pressure is like 2.8 megapascals, and what is your liquid phase and vapor phase composition? Like you have a 50-50 is the overall solution composition, but when you are in the two phases, so in the liquid phase you have 30 mole percent propylene and 70 is hexane, whereas in the vapor phase you have close to like a 65 or 68 mole percent propylene, and the rest is the hexane. So this is a vapor, liquid. So liquid and vapor are in equilibrium. As you go up with the pressures, like you see the tie lines shrinks down. Then once you hit the mixture critical point, tie line becomes like a point. It's not there is no distinction between vapor and liquid phase. Now let me show you the binary mixture densities. So here the density on the y-axis and the x-axis is pressure. So what happens is like let me go back to a couple of more slides. So here, starting at this, like you're at a fixed temperature, starting at this bubble point pressure, you increase the pressure continuously to all the way to like 70 or 100 megapascal, and then at each pressure, so you record the density. Like that's so I have a calibration curve, and then I know the mass of the binary mixture, so I can kind of calculate the density of this mixture. So this is at 25 degrees C, the circles, and the squares are at 50, and the diamonds are at 150, this is 250. As temperature increases, the density decreases. This is a kind of typical phenomena, because as temperature is increasing, the molar volume increases, so the molecule, the phase expands. But as the pressure increases, the density is increasing. That means like you are compressing more and more the molecules together, so you are increasing the density. Then after we measure this experimental data, then we use like a standard Peng-Robinson equation of state as a model for calculating the phase behavior and density. So this is a Peng-Robinson equation that we see in chemical engineering textbooks. So this is a cubic form, like in volume. So We can use, you can write your own program to model, to calculate the bubble point pressures and dew point pressures, and also the mixture densities. This is a widely used equation of Tait, and it's relatively easy to implement or write your own code. Also, it's available in many commercial software programs. Though some drawbacks are there, and it doesn't predict the liquid density that accurately, especially for larger molecules, and it requires critical temperature, critical pressure, and eccentric factor as the input parameters. If you don't know for a molecule this properties, then it's a little difficult to use this equation of Tait model. But for the system that I showed you, for the hexane propylene, it's like for both compounds, you know the PC, PC, and the eccentric factor, so you can kind of easily calculate the phase behavior and density.
Okay,
I'll show you.
Give me a moment.
I'll show you at the end of this talk how to do the calculations using the Excel. And now let me show you density and viscosity. So it's like the viscosity is a transport property, and these kind of properties are really important for calculating the amount of petroleum or reservoir available in the reservoir, and also to model the flow characteristics when you are extracting the oil from the ground. So currently oil companies using the correlations based on low temperature, low pressure data, and those data are unsatisfactory and are not reliable, and they cannot predict the addiction condition, and the accuracy goes down, and it's only plus or minus 50%. So this is the National Energy Technology Laboratory, and we have a collaboration with them. Then we measure the properties of simple hydrocarbons at extreme temperatures and pressure. So what we use is high temperature, high pressure rolling ball viscometer for measuring the viscosity. So this is the cell body. It's pretty long, like it's 12 inches long. And then there's a 5 window, the ball. So the ball goes inside and then it rolls. And this is a small window folder. So it has a couple of parts, like there's a window cap, and there is a sapphire window, some O-rings. And what we use is we put this together and then stick it into one of these holes. And then there are like 2 on this side and 2 on the other side. We shine light from one side. There is a light detector. I'll show you that in a schematic. And this is a real apparatus in our lab. And there is a pressure generator, and this is a cell. There is a data acquisition programming. So in this schematic, this is so that I showed, like there are 4 small window holders. So you shine light from one window, and then you record or you detect the light on the other side. So the light we use to detect the ball motion. So what you do is you have the cell, exactly what I showed you for measuring the density and phase behavior, but this is a little bit longer. Then you have a ball here, and this borescope and the sapphire window to look inside the cell. And the back end is like a bellow and then connected with an LVDT rod. So now when you have a ball and you put a fluid, then you tilt it, you tilt the table, then the ball starts to roll. As it is going and coming, when it blocks this light, then the data acquisition program starts to record the data. Then when the ball leaves this second set of port, then the acquisition starts, and then we measure the roll time between these 2 sets of windows. So that gives us, we know the density, we know the distance between these 2 ports accurately, then know the time, so we can kind of calculate the viscosity. So the viscosity equation is given by this equation. So there is a constant, this is specific to the instrument. So it's called Viscometer constant. The density of the ball that we know, density of the fluid, you measure or you take it from literature at a given state condition, state points, like at the temperature and pressure, the sign of the angle, so the angle that you lift the viscometer, and if V is a velocity, it's a ball velocity. The velocity is like a length over time, so length between the two ports is fixed, so that's why we have to move the length into K. So K over L is a constant. Then the viscosity over time, density of ball, fluid, and sine theta. So like in the our density meter, so for viscometer also you need a calibration curve. For a fluid whose density and viscosity are known, then we put that fluid into the viscometer and then we measure from 25 to 250 degrees C the ball roll time at different pressures. And then if you know the roll time, you know the density of the fluid, you know the angle, you know the viscosity of the fluid, you calculate the K. So the K versus pressure you generate. And see, interestingly, from temperature 25 to 250 degrees C, there is no effect on the K. So that means K is only dependent on the pressure. So it's and then knowing this K, then for an unknown fluid or for a fluid of unknown viscosity, then you know the K, you measure again the roll time, so you calculate the viscosity. That's what we do. And we took a simple system like a toluene, and this is a literature diagram showing the pressure on the x-axis, y-axis, and temperature on the x-axis. See that there is a lot of high pressure data below 100 degrees C. But once above 100 degrees C, it's very hard to measure this data. And then we are interested in getting the data under these conditions, like the temperature all the way to 300 degrees C and pressures to 300 megapascals. So we measure this apparatus is able to measure both the density and viscosity simultaneously. So we measure the density at three different temperatures, 50, 150, and 250, all the way to 300 megapascals. We compare our density data with the NIST. It's the National Institute of Standards and Technology. And then our data is right on top of NIST, like the deviation between our experimental data to the NIST is like plus or minus 0.75%. So that means under this condition, this is a pretty good and reliable data. So, and then the accumulated uncertainty is like 0.8% with a coverage factor of 2. And then we modify, so you measure the density at these three particular temperatures, but if you want to calculate density at other condition, like let's say 100 degrees C or at 200 at a different pressure where you don't have a data, then you need to model or you need to develop a mathematical correlation. So we use a correlation called Tait correlation. This equation is given with this formula. And then you write your own simple Excel functions to calculate the density. And then once you have these parameters, like these coefficients, then you should be able to calculate at any given temperature and pressure. And then from this data, like you can also generate the compressibility factor data. That is like a derivative of this density with respect to pressure at a constant temperature. So this is important for, especially for oil and gas companies, for estimating their amount of oil. And then this graph shows the viscosity of a toluene pure compound with respect to function, with respect to pressure. The pressure on the x-axis and then viscosity on the y-axis, and from 20 degrees centigrade to 260 degrees C. These are all different temperatures. And then going from like all the way 10 megapascals to 300 megapascals. So, and we also submitted this for the Journal of Chemical Thermodynamics, and it is still in review. So now the technique is like, as I showed you in the literature, there is a lot of data for toluene below 100 degrees C. and pressures to 300 megapascals. So we use that data to validate our instrument and our technique. Then we measure the original data about 125 degrees centigrade and pressures to 300 megapascals. Then once you have a viscosity data, then again, as I mentioned, for the density, for viscosity also you need to, like if you have a model, so then you should be able to calculate at different conditions, at other conditions, whatever you are interested. So the viscosity, we use free volume theory, FVT. So in free volume, the viscosity of a fluid is given as a sum of two terms. It's eta 0 plus delta eta. So eta 0 is a dilute gas viscosity. This comes from the well-known like a kinetic theory of gases. Then the delta eta term is given by this big expression. And here the three fitting parameters are L, alpha, and V. And then density is fluid density at a given temperature pressure. That either you should know from experimentally or you can calculate using equation of state. So here, so the advantage of this modeling is, like if you have a small amount of data, at let's say a couple of isotherms for viscosity, then you get your L alpha B by correlating to the experimental data using PCSAT or Feng-Robinson as a density input. Then you should be able to calculate the viscosity in the entire temperature pressure ranges. So for toluene, we compared our data, the literature, then this is like within 3% of average 3% our data compares to the literature. That means like the model is predicting the experimental data very well. So I'd like to kind of conclude this talk. It's like, so high pressure, high temperature, phase behavior and density data is really important for process design as well as to verify equations of state calculations. And also it's the viscosity data is important for estimating the pipings and flow properties, and to estimate the amount of oil present in the reservoirs. And for chemical engineering calculations, like we use a Visual Basic that is built into the Excel as a tool for doing all this calculation, and as you guys can use as a tool to teach the programming skills to the students. There's a couple of reference books. This is an introduction to chemical engineering thermodynamics, Smith and Vaness. This is what we used as a reference in Osmania University. And here at VCU, so we use this chemical and engineering thermodynamics Sandler as a reference book. Both are pretty much covers the same concepts. And there's an excellent book with the engineering with the Excel. This book is specifically made for like a chemical engineers. Like it talks about all kind of calculations and gives a very good overview of Excel VB strengths. And then there's a lot of open literature, open source material available, especially there's MIT. They have so many courses, and in chemical engineering there is thermodynamics, separation and unit operations, all sorts of things you can use. Nowadays most of us have internet access, so you can look into like what they are teaching and what the content is, so you can show to the students. Just it will help them understand better. And also the scientific papers like education for chemical engineers. Here they say that okay, teaching XLVBA as a problem solving tool for chemical engineering for courses. So you can also check this journal for different papers. Okay, now this is my end of my talk, and I'm happy to answer any questions. But before taking the questions, let me show you one thing, like how we use Excel for calculations. So most of the nowadays even students also have the computers, and they hopefully they have Excel. So the Excel has a built-in feature called a Visual Basic. So you can use that Visual Basic for programming simple calculations. For example, here I'll show you the one thing that we commonly do. So this is experimental data: temperature, pressure, density, viscosity. And you take this experimental data, and what I showed you in the at the end of my talk, the free volume theory, L alpha B. So you fit this experimental data to get your L alpha B. So how do we do that? So you have all sorts of that equations. So here is the equations for the free volume theory. So you need some input parameters. So by having these equations, so now you can go and then make your own program. So here is how the program looks like, and so it's not a pretty extensive like a program, but you can write all the steps in the calculation so that you can do routinely. Like okay, here you can come and then call your function, then define all the variables, so then it will returns you the answer. So this is kind of pretty cool for doing chemical engineering calculations, and it's really helpful for students for learning their programming skills. And it's like you can show even simple things like for example the plotting, like you do the common thing, the graphing. So here let me show you. So if I say run, then it asks like where do you want to put the graph, then what is your data. So plots. So that means, I mean, we can do this directly from making a graph tool, but like just if you write your own code, little program, so you should be able to. And there's a lot of information available on the web, and also the books. Like you can see that, then you can play with it for making your daily needs. Yeah, that's all I have to show. Now let me take any questions you guys have.
Thank you, sir. The attendees can type their questions and send it to us through the chat window.
Yeah. Yeah, I opened up the chat window. Oh, there is a questions. Yeah. You don't see me right now? Okay. So Sridhar, do they have like a voice access, or they just only type in the computer?
Only text, sir.
Only type in. Okay. So how many people are there? Like 13?
14 were there till now.
Okay. So as you mentioned, these are all like a faculty.
Yes.
Okay. Yeah, that's why I made my presentation more like the kind of research that I'm doing, so that it helps them to understand, like what to
Yes,
teach to the students. It's not like I don't want to make it more like a regular engineering class. It looks like there are no questions.
yes, sir. Just give them 1 more minute and then okay.
But they can hear my voice, right? I mean, of course.
Yes.
Yeah. So how many webinars you organize, Sridhar?
Till now, maybe about 400 or 500.
Oh, like per week, like definitely you have like one or two.
Ah, definitely.
Okay.
And weekends there are classes going on.
Mhm.
4 or 5 classes are there.
Okay, okay. So are
All
there
through this mode.
these classes directly to the students, or it's only always to the faculty?
This is faculty development.
Faculty.
Directly students, that is initially that was the focus, but
Mm-hmm.
teacher training is being done more now since the
Yeah.
last 3
And
years.
that's also important, especially if you take this new engineering colleges.
Yes, sir. And they also good demand.
So, like many people are interested in this, like, or
In which part, sir?
yeah, in this kind of webinars, like, are there many people show interest, or like not much?
Yes, yes, definitely. Now, I think this week, Christmas week, so that's why attendance is a bit low. Otherwise, 50 to 60 people at least are there.
Mhm. And another thing is this chemical engineering compared to other computers or
Yes,
IT
yes.
kind of
There will
stuff.
be
All
lesser
the
people.
colleges have that course, you know.
Yes.
And chemical engineering, when I was studying back in 1998 and 2000, so only 700 students all over our two
Uh-huh.
states, UP and Telangana.
Uh-huh.
But yeah, now they increase little bit, like 1400 or something.
Yes, yes.
Yeah, it's not.
And other college also have many other colleges also came.
Yeah, yeah. And now, especially you said this is overall India, means I expect many people.
Yes, but after that, I get a lot of requests for the recording, sir, because timing is also a little late and holidays time also. But
Ah,
by email, I get requests for the recording
okay, okay, okay.
because the weekly mail goes out to thousands of people, and whoever can make it, they try to come. Otherwise,
Oh,
they know the recording is available.
oh, okay, okay. I
It is
understand.
better to attend live because then they can ask you questions.
Okay, okay.
I think it is still because it's a Christmas week.
Oh, yeah. And can you also please send me the link for the
Yes, yes,
recording?
yes, yes. In within 1 hour, I'll send it.
Okay. You know, yeah, I also like to do something with the Usmania University, like some of my professors
Uh-huh.
have been asking like this, but maybe we need to think of something.
Correct.
I should have sent this like information to them so that they can attend.
Sure, sir. All this email is accessible to anybody who is interested in the webinar. Like anybody can attend live.
Oh, okay, okay, okay. Yeah, because nowadays, like internet is quite common everywhere. I think all the colleges are giving the internet, you know,
Yes, yes.
even
And
students.
many people they are organizing their lab also to for more people to watch in the same computer.
Oh, okay.
Project it on lab and they watch.
Mm-hmm.
So, okay, sir. Thank you. So we run out of time, and I will send you the recordings.
Okay, sure. Thanks. Yeah.
Thank you.
Bye-bye.